First, I'd like to begin by giving an overview, the problem statement of the problem statement. One, highway on-ramp congestion is one of the major challenges in urban areas. It increases fuel consumption and therefore increases the emissions that the vehicles produce into the environment. It also increases travel times and reduces the highway average speed and throughput. It's also a major cause of accidents. Currently in research, you can find that supporting arguments for platoons being an effective way of combating congestions on the highway. For example, Carsland et al. In 1991, they suggested that homogeneous platoons can increase highway capacity by up to 4-fold. Emzabat et al. In 1994, they say platooning may reduce air drag on vehicles by up to 40%. This reduces the fuel consumption by these vehicles and also consequently the emissions. In mixed traffic scenarios, however, there is a quadratic distribution between the capacity, lane capacity, and the market penetration rate of automated vehicles. This was reported by Su et al. In 2014. In 2018, one of the latest research in this field by Mena et al., 5 to 15% reduction in traffic flow and speed was observed when platoons were allowed to maneuver, such as changing lanes, merging, and splitting, as opposed to when they were not. These reports suggest one thing. These reports suggest the following. Vehicle platooning is beneficial to traffic flow and the environment. However, these benefits are tied to the market penetration rate. This brings us to the argument whether we should apply vehicle platooning in a homogeneous setting versus heterogeneous settings. Also, unstructured maneuvers further reduce the benefits of platooning. Now, let's take a brief introduction to what platooning really is. Vehicle platooning is when two or more vehicles travel together at synchronized speeds by trying to maintain a constant gap between the vehicles. The advantages include improving traffic flow dynamics, travel speed and time, road and highway throughput. It also reduces the fuel consumption and emissions. It improves the safety because human error is taken out of the equation. Now, some of the drawbacks. Vehicle platooning is expensive infrastructurally. The benefits are closely tied to the market penetration rate of automated vehicles, and there are also public concerns regarding automated vehicles traveling side by side with human drivers. The technology at this point is also not fully mature. This picture would show an illustration of how platooning occurs on the highway. Now, because it's not easy to achieve vehicle platooning in real life with, you have to be part of a major project to actually execute a project like that on a large scale. We implement vehicle platooning on simulation software in order to observe the impact of such platooning applications on a network. The framework of choice that we use is Plex Sumo. Plex Sumo is the framework of choice we use is Plex Sumo, which is an open source road traffic simulator. Omnet++ is used for the simulation of communications between the vehicles. And for platooning applications of these two frameworks, we use Plex Sumo and Plex Veins, as you can see in these in the diagram here. This aspect represents a Plex Sumo version where we simulate the movement of vehicles, and the Omnet++ network simulation aspect gives us the opportunity to simulate the communications between vehicles. Now to the model that was designed for this study. The optimized departure plane model is made up of three key components: the plane class, the simulator, the parameter files and utility functions on the one hand, chassis, as can be seen in this diagram, acting as an intermediary between the the simulator, the class, and also the framework as discussed above. Then we have the Plex Sumo and Plex Veins on the other hand, including some output XML files. Key among the functions of the plane model are: 1, the formation of lane and destination specific platoons; differential speed control, speed and spacing control; lane change, flag search, and cooperative lane change maneuvers. 2 safety protocols are also included in this model. The first lane check estimates the arrival of platoons to conflict zones of both departing platoons and already existing platoons in the network, to ensure that when platoons are departed at a certain time within the simulation, they will travel from their destination to from the source to the destination without any collisions. The second check ensures collision-free transit by comparing the trajectories of the departing platoons and the existing platoons in the network. The simulation setup, scenario setup. There are 3 scenarios that are studied in this particular study. The ACC scenario, which employs the cross-car following model for car following. The original plane model, which represents a previous study proposed by the authors of the study. And then the optimized departure plane model, which employs dual safety check protocol for lane-specific departures. As can be seen in this diagrams, this is the network of the model. There are 4 sources where vehicles are able to depart from, platoons are able to depart from. There are 3 lanes, platoonable lanes, that have different lane velocities, allowed lane velocities. The difference in lane velocities allows for the platoons to arrive at lane change stations separated spatially and time headway to allow for lane change transitions from higher lane velocities to lower lane velocities. So at this point, platoon 3 will step down to the second lane, while platoon 2 will step down to first lane, and platoon 1 will step down to the last lane, which is the exit lane to exit the system. As can be seen, the first platoon arrives at its destination. The second platoon steps down onto the next lower speed lane and continues towards its destination, which is sync 2. And then platoon 3 also steps down from the highest lane velocity to the second highest and continues towards its destination, which is sync 3. As can be seen in this figure, the farthest traveling platoon approaches its final lane destination station. And while all of this is happening, there is the dual check protocol, which is estimating at the particular point in time where it will be ideal for a particular lane platoon to be departed. When we do this, what happens is that we are able to control exactly when a platoon is departed. We are able to control the travel speed and the travel velocities of the complete network. Now to the results and analysis. Because of time constraints, I'll go straight to the point. With the ACC scenario, you will observe that these are a lot of lane changes, rampant and unstructured lane changes occurring. With the original plane model, you can see that we have limited the number of lane changes to 24 simultaneous lane changes at an instant. Between these lane changes, you would notice long periods of time where there were no lane changes that were permitted. This allows for a smaller number of lane changes to occur during the transit. For the optimized departure lane change model, you would notice that apart from the 24 simultaneous lane changes, there are spikes of more than 24, but multiples of 24 lane changes, because at any point in time when the system observes that it is an ideal time to depart a vehicle, a particular platoon on a particular lane, it is departed. So there may be more than 24 vehicles per platoon in the system at any given time. The total number of lane changes in that particular scenario is 4,008, compared to the 22,809 lane changes that are allowed in a normal setting. Then we also observed the average travel time. By the closing of the simulation, which is 60 minutes in length, we observed that the travel time, the average travel time from source to destination of a particular platoon was around 22 minutes. That in the original plane model and the optimized departure plane model are around 8 minutes respectively. You can also observe that this is increasing with time, whereas we are able to stabilize the travel time around 8 minutes for both the original plane model and the optimized plane model. This is significant. It means that we will be able to predict just how much time that a particular vehicle or platoon is able to take from source to destination, and we will not have to worry about the situation of congestion at all. Again, with respect to average travel velocity, because of on-ramp and main trunk congestions, you would realize that at the beginning of the simulation, the average travel velocity increases all the way to around 45 meters per second and gradually goes down again to around 10 meters per second because of congestion. However, when we compare that to the original plane model in our case and the optimized departure plane model in the new in this particular study, you would realize that the average travel velocity is capped around, it stabilizes around 55 meters per second. This is significant as well, as it points towards around 243.75% improvement in travel velocity in the original plane model and the optimized departure plane models respectively. With respect to throughput, we analyze the number of running vehicles and the number of arrived vehicles. For the ACC scenario, you would realize that the total number of vehicles that arrive at the end of the 60-minute simulation time is 2,100. For the optimized, for the original plane model, we have around 2,500 vehicles arriving by the end of the simulation. And with the optimized departure plane model, we have up to 3,200 vehicles arriving at the end of the simulation. This signifies around 52.4% increase over the original, an ACC scenario, which is in most cases a lot better than traditional traffic where humans drive the cars. Also, the original plane model maintains a 19% improvement over the ACC scenario. How are we able to do this? Because we are able to, the blue line here indicates the number of running vehicles, and the number of arrived vehicles is the one in red. What you observe in the ACC.
So yeah, we can use to complete, please.
Okay. What you observe in the ACC scenario is that the number of running vehicles increases simultaneously as the number of arrived vehicles in the ACC scenario. We're able to hold that down to around 500 vehicles in both scenarios here, while we allow the number of arrived vehicles to increase. This frees up the highway, and this allows us to have travel velocities as high as 55 meters per second. We analyze the amount of fuel consumed as well, and this would indicate, as you see in the ACC scenario, we have the average fuel consumed during the simulation at any instant is around 3,200 milliliters per second in the ACC scenario. This number goes down to around 1,200 in the original plane model and 1,400 in the optimized departure plane model. Now, this does not mean that the optimized departure plane model is not as efficient as the original plane model. What is actually happening here is that there is, because of the optimized departures, there are more vehicles that enter the system as time goes on. So you'd notice that the number of the arrived vehicles in this particular scenario was more than that in the previous model. So this accounts for the increase in the average fuel consumed. You would also notice a similar pattern between the amount of fuel consumed and the emissions produced. This is because there's a direct correlation between the amount of fuel consumed and the emissions that are produced. So of course, we make also a lot of savings in emissions when comparing the original plane model and the optimized departure plane model to an ACC scenario. This table will give the improvements of, say, for example, carbon dioxide in the original plane model versus the ACC scenario, and the optimized departure plane model versus the ACC scenario. These are good improvements over an ACC scenario, which is already a lot better than traditional traffic. In summary, this study has proposed an optimized departure strategy for the plane model proposed in our first study to improve the throughput of the model. A dual-check departure protocol for the platoons was proposed in the study, and the protocol ensures the departure of platoons at the earliest possible time while guaranteeing collision-free transit from source to destination. The new model significantly improves the previous model in throughput and comparable in terms of all other agencies of evaluation. Thank you. And I'd like to invite any